we have another intro video. This just covers a little bit that the other one doesn't. We're going to take a look at properties, examples and non-examples, and we're going to look at parts of the equation. The graph of a polynomial function, we're just going to call it px, has the following properties. The domain of a polynomial function is all real numbers. So if you have a polynomial function and we ask you for the domain, all real numbers every time. The polynomial function is continuous for all real numbers. There are no breaks, holes, interruptions, or jumps in the graph, which again kind of reinforces the fact that the domain is all real numbers. If there was a break or a hole or any kind of interruption or jump, the domain wouldn't be all real numbers. The graph of px is a smooth curve with rounded corners and no sharp corners. That's kind of a sneak diss to absolute value. That's the only graph I know with a sharp corner. It's smooth, rounded corners. The graph of px with degree n has at most n x-intercepts. And we're going to talk about how you get the degree of the polynomial pretty soon. But for a great example is quadratic equations are great examples of polynomial equations. It's a second degree polynomial. And if you know anything about quadratics, you know that it can have no intercepts, it can have one intercept, or it can have two intercepts. So that's why it uses the language at most. The graph of px with degree n has at most n minus 1 turning points. Again, we have the at most here. So is this a polynomial or not? Well, there are no breaks. It seems to continue forever. It has nice rounded corners. So I'm going to say, yes, this is a polynomial. Is this a polynomial? Well, the one thing that we have here is that we see a sharp corner right here. So with that sharp corner, we're going to say, no, it is not a polynomial. Is this a polynomial? Well, it seems to go on forever. It has nice rounded corners, no breaks. Yes, this is a polynomial. Is this a polynomial? This is that quadratic we were talking about. If you know what that looks like, automatically, we know that that's a polynomial. It's nice rounded, has no breaks, looks like it goes on forever. Is this a polynomial? Well, there's an asymptote here, which means there's a break. There is, the domain is not all real numbers because there's an asymptote. So I'm going to say no, not a polynomial. Is this a polynomial? Yes, looks like x cubed. All right, so here are some more examples and non-examples of polynomials. On the example side, we see that we have negative 4x to the 4, 2x to the 3 minus 6x squared minus 12x plus 9. You're going to see a lot of polynomials in that form. They're all whole numbers there. You'll notice that there are negatives, but the negatives are not in the exponent. The exponent has to be just whole positive numbers. Fx equals 0.3 times x plus 3 times x minus 8 times x plus 1 to the third. This is also a polynomial. It's factored. You do see a decimal there, but the decimal is not in the exponent. Here we have a quadratic function right here. We already know that's a polynomial. And here we have a linear function, which is also a polynomial. These are all examples of polynomials. Now here's some non-examples. Now in the first one, 2x squared plus square root x. This one is going to not be a polynomial because of the square root. X cannot be inside of a radical. Now if it was root 2x squared plus x, that would be okay because the radical is just over a constant number. The x cannot be inside the radical. For the second one, what can you spot here that makes this not a polynomial? If you said it's the negative in the exponent, then you are correct. No negative exponents allowed. Can you spot what's wrong with this one? Well, we have an x in the denominator, which is the same thing as having a negative exponent. You could express that as x to the minus 1. So there are no x's in the denominator. Can you spot why this is a non-example? Why this is not a polynomial? It's because x cannot be in the exponent. And last but not least, we talked about fractions before. This is not a polynomial because the exponent cannot be a fraction. So let's take a look at parts of a polynomial equation. First thing I want to talk about is the leading term. Now in this particular example, the leading term is cubic. It's 2x cubed. The leading term is defined as the x that has the highest exponent, or I should say, in case it's not x, the variable with the highest exponent. Looking at this entire thing, the highest exponent is 3, so that is going to be the leading term. Usually when they're put in order from greatest to lowest, it's the first one. Part of the leading term is the leading coefficient, which is the number part of the leading term. This will affect things like end behavior and how far the graph is stretched vertically. That 3 up there is the degree of the polynomial. That's going to determine whether the polynomial is even or odd, and as we mentioned before in the properties, that's going to determine how many terms the polynomial can have, and it's also going to determine how many x-intercepts the polynomial can have. Last thing I want to talk about is the constant term. It's the term that does not have a variable on there. That is mainly going to affect the y-intercept. It can also affect the possible rational roots when we get into it. So here's a practice. Given the following polynomial function, state the leading term, the degree of the polynomial, the leading coefficient, and the y-intercept. Alright, so according to what we just learned about parts of the polynomial function, the leading term is going to be 7x to the 4. The 4 in the 7x to the 4 is going to be the degree, and the 7 is going to be the leading coefficient. The y-intercept you get from the constant. Y-intercept is going to be 0, 6. You have to remember, y-intercept is where x is equal to 0. So it's easy when it's in this form to put zeros for x. When you put zeros for x, you get 0, 0, 0, 0, and you're just left with a 6. Alright, we're again going to find the leading term, degree, the leading coefficient, and the y-intercept. So in order to find the leading term, it has to basically be in the form of the one that we previously did. But instead of FOILing everything out, which will take an extremely long time, we're going to take the leading term of each one of these and multiply them together. So as you can see here, we have the 3x, the 2x squared, and the x cubed coming from all the leading terms of the factors. We multiply those out, and we get 12x to the 6. Remember, when you square this, you're going to get 2 squared, which is 4. So for all the constant values, we have 3 times 4 is 12. For the x's, you can count them. We have 1, 2, 3, 4, 5, 6 x's. So that's 12x to the 6. Basically, you're adding up all the exponents. 1 plus 2 plus 3 is 6. So that is my leading term. And from the leading term, I can get the degree, and I can get the constant term, the leading coefficient, which is 12. Now to get the constant term or the y-intercept, we're going to plug zeros in for x. So here we get 3 times 0 plus 2 times 2 times 0 minus 7 squared, and then 0 plus 2 cubed. Which leaves me with, if we cross out the zeros, 2 minus 7 squared, 2. Calculate that, you get 780. to get my y-intercept, I replace all my x's with zeros. Now, I get them over here, but because we have an x multiplying everything, that's a 0. The entire thing is going to be 0. Which means that my y-intercept is at 0. And there is no exponent here, so that has a multiplicity of 1. Here you can predict what's going to happen. This is going to give me 0. So if I put x minus 3 equals 0, that means I get x equals 3. And because we have a 2 up here in the exponent, it has a multiplicity of 2. Now you might be asking yourself at this point, okay, you told me how to find multiplicity. What does multiplicity do? Let's explain. So multiplicities basically tells you how the graph is going to act at that 0. So if it's an even multiplicity, it's going to act like x squared. Or if your multiplicity is any other even number higher than that, x to the 4, x to the 6, x to the 8, they pretty much all act like x squared. So if that's my 0, you can see how it touches the 0 and turns back up. It looks like a quadratic graph. Now that can either happen above the x-axis, or it could also happen below the x-axis. Now what happens if it's an odd multiplicity? Well, odd numbers like 1, 3, 5, and 7, they will all go through the x-axis. Now the only difference here is if it had a multiplicity of 1. If it has a multiplicity of 1, and this is my x-intercept, it's going to go straight through like a linear line. Straight through. It's not going to curve, be very curvy. But if it's 3 or above, it's going to have that kind of sigmoid shape that x cubed has. So it can either go through from top to bottom like that, or it can go through from the bottom to the top like that. Again, if it's a multiplicity of 1, it's going to go straight through. If it's 3 or higher, it's going to have that sigmoid shape. So let's take a look at our example that we found multiplicities for. So we are expecting to have a 0, at -2, and at 3. When it goes through -2, we're expecting it to go straight through. When it goes through the 0, we're expecting it to have a curve to it. And when it goes through 3, we're expecting it to bounce and go back. So let's see what the graph looks like. Here you can see it's going straight through at -2 because it has a multiplicity of 1. It has that curvature at 0, looks like an x cubed graph at that 0. And here we can see that it looks like a quadratic function at that 0. So that's how multiplicities affect the graph.